Hello and welcome to this session of the Data Platform Virtual Summit 2022 edition. You know Transact SQL? Well, you're in the right room. We're going to be doing some real-time data processing with Azure Stream Analytics. I'm Florian Eiden, a product manager at Microsoft in the ASA team. So first, I wanted to talk to you a little bit about near real-time analytics and stream processing, which is the domain that Azure Stream Analytics enables. Talk to you a little bit about the product, and then go into like streaming SQL, our flavor of T-SQL that applies for stream processing, and kind of the three high-level aspects that you need to know about, which are type management, how it differs in Stream Analytics compared to SQL Server and Azure SQL, temporality of stream processing, and like some performance considerations. Because we relate to costs, which is an important aspect of cloud. So near real-time analytics, the big question here is what it is. So usually we define that term speaking about applications that require latency going from milliseconds to minutes. So that's from whatever happened to the time where you generate an insight. So either a new row, an alert, a notification, some data moving on the dashboard. That's milliseconds to minutes. That's where we are. And why that low latency? What's interesting into that? So quite often it applies to domains where there's a short shelf life. So there's a time to live in terms of either the data that's coming in or the insight that you can generate out of it. So an alert, there's something going wrong, there's something burning, that's something that's going to burn. You need to notify a user that's their attention is required. You have an anomaly going on, or you're detecting frauds. Like, you need to react quickly to those. So those are the usual applications where near real time really shines. But also not only, so that's the starting point, but most often now we see applications around the fact that business processes are now happening in real time. So even when you think about an inventory reconciliation, when you think about payroll in HR, those are inherently batch processes, like monthly payroll that happen every month. But that doesn't mean that you don't want to have a real time or a low latency view of where you are all along in the month. And only at the end of the month, you issue that snapshot. So a process that we are usually considered batch, now more often than not, we say, no, actually, you can have a current view of what's going on. And what's batch is only the snapshot that we do periodically. So most business processes now, we're realizing can happen in real time. And also most of those like workflows are now being automated. And those are now services or microservices talking to one another. And for those, they don't need to wait. They can just be implemented with like reactive solutions, just changing one bit of logic after the other. And you can go low latency for that too. There's no benefit in just waiting for a human being to be there in the room. Like, everything's automated. You can just go as fast as you can. As part of near real-time analytics, there are multiple technologies or like approaches to solve that or solve the requirements in those domains. One of them is stream processing. So stream processing is linked to streams, obviously. And what streams are is like continuous flow of events. So if you think about a table in SQL, that's what we can see as data at rest. So you have a table, you put rows in, and at a single point in time, you have a contained set of data of which you can take a snapshot, and you have all of the data that's there sitting nicely, and you can issue queries against it. For streams, that's not the case. You're looking at data that's continuously being emitted, continuously being appended, ever growing, and it's data in motion. And quite often you have a limited retention. So you only have access to 1 day of history or 7 days of history, just because there's so much data that you cannot copy everything. It doesn't make sense. And data also, as I mentioned, has a short shelf life, usability. So you don't if you haven't found out that your factory was going to burn in 15 minutes, then it's burnt and you don't really care about the data from last week. So really those are all intensive that makes like streams really like short-lived, high volume, ever growing, and data in motion and not data at rest like a table in SQL. The other important aspect here that differentiates stream processing to other near real-time or real-time techniques or approaches is that in stream processing, those events, they are what we call facts. As in, you can think about it as like a fact is a fact table, like something happened. And anybody can subscribe to that to learn that something happened and react and build something on top of that. These are not intents. So when you need to comment, so send a comment to a device or like between multiple subsystems or like a point of sale, talking to an inventory management system and telling them that to put and send that to shipping. Those are commands and jobs. They have intention between each messages, behind each messages. Those are not like solved by stream processing. So that's like service bus and EAI, like those kind of systems. So we are in stream processing, and what we are doing is extracting value from those streams. So stream to apps, alerting derived events, stream to data store. So that's the streaming ETL pattern, extract, transform, and load. And streams to the human eye. So that's real-time reports, real-time dashboards, and notifications. And the service in Azure to do stream processing is Azure Stream Analytics. So it's native, it's Microsoft, like it's a first-party service in Azure. It's in platform as a service, and it's been there in prod since 2014. So it's not like we are new or just landed. Like this is a robust service that's been in production with like 3 nines, 4 nines for some times now. It's based on Trill, which is an open source now library that was made originally from Microsoft Research, so like pretty high-end stuff. And really we want to make stream processing as easy as possible, which is not easy. But we hope that the service is like, we are trying as much as we can to make the service as easy to use and operate as possible. Serverless, low code with SQL, well integrated in Azure, with both VS Code and the portal as developer experience, CI/CD capabilities, the whole stuff, the whole story, and easy to run with easy to understand pricing, etc., and available pretty much in every Azure region, should be. And pretty much what you're doing is writing a SQL query. So let's say your business case is, I want to know when an equipment has its average temperature per minute above 75 degrees. This is the SQL query. It's just like, you know how to write those. So select with an average, group by, having clause. The only thing that's a little bit newish is the tumbling window. So the tumbling window just apply the temporal component of that query. And we will be discussing about that and the other differences on the SQL we offer to T-SQL. So you know exactly how to figure those out. In terms of canonical architecture, so that's how you will build in terms of solution architecture, how you will build a solution with Stream Analytics. The important aspect is we read data from stream. And you can think of it in terms of a model. That's a table. A stream is a table. Just have like specific properties, but it's a table. But due to those specific properties, that table is not stored in a relational system. It needs to be stored in an event broker. So it's a table. It's pretty much a queue. It's in between a queue and a table. But yeah, okay. It's just a thing on which I can write a SQL query, and it's going to be in the from clause. So yeah, pretty much if you know SQL, that's a table. But it doesn't live in a relational database. It needs to live in an event broker. So for us in Azure, that's going to be Event Hub, IoT Hub, or we can make do with Blob Store. But this is more like for history processing. Like live traffic should go through Event Hub or IoT Hub. Think of it. It's a table. Don't worry too much about it. There's one thing that you need to know about it, and that's different. And I will talk about it a little bit later. So your producers, be it devices, whatever logs or files like customer data transactions or your business line of business applications, they need to send their data to that event broker. They need to find a way to do that. Okay. Once the data is there, I can write a SQL query against it in Azure Stream Analytics. So you go in the portal, create a new Stream Analytics job, write your SQL query, declare that is an input and an output. And you pick one of the output that you want that ties to your business application. an event hub, another event hub. If you want to do event hub to event hub, an Azure function, you need to send like an alert or a text or whatever, a logic app. Of course, if you want to do data warehousing, either like a data lake, storage, SQL, whatever, or real-time dashboarding using Power BI. So an input, SQL query, and output. And let's focus on the middle piece, like the job. What's a job? So a Stream Analytics job is what you will be creating. So let's say you want to do that. You want to write that SQL query. So you will be creating a Stream Analytics job. Inside of that job, like the important aspect is you will define a single streaming query. So a single statement, potentially multiple, like we will see. I'll go into there. A single SQL statement. This job will have properties. One of them that's really important to know about is like the scale. So how you define the scale of a job, so that means the performance, how much you're going to pay and how much performance, how much latency we'll get out of it, is by using what we call streaming units. We will be talking about that a little bit more. And usually when you think about a streaming solution, you may be chaining jobs. So you may have a first job that's going to be a little bit of processing, output to Event Hub, being read by another job, Stream Analytics job, that then will output to SQL and Cosmos DB. And that's going to be your whole package. But you can have two jobs, multiple Event Hub, that's what you need, and a couple of outputs. That's how it is. Sometimes you can put everything into a single job. Sometimes you need to split into multiple jobs, and we will see why. You define your job, you create your job, you test, you do local runs, you pay nothing. Only when you start the job will you start paying for the running job. The second artifact object that we have is the cluster. We only have two objects, job and clusters. And it's basically just a hosting environment. So if you need like VNet support, or if you need like a single tenant, like dedicated environments, that's the solution we offer. And it's just a property of a job. So you take your job, it was running in multi-tenant, like normal deployment, you needed like customer, like VNet support. You just added it, changed the property somewhere that says now it's attached to a cluster that I've created before. And then when you start it, it's going to start and run in that private cluster. Now what you pay is not by job anymore. You pay per cluster. So just I want you like to be aware of like that aspect. Okay, drilling down into a job. So a job, what does a Stream Analytics job consist of? A single streaming SQL query statement. At least one output, obviously you're reading from somewhere, and at least one output, obviously you need to write somewhere. So that specific scenario that's being illustrated there. So we have incoming transactions from my e-store that are checked against a product reference table. So I'm doing a left join basically on the product ID. Either I have a match and I can find that product ID, which should be the case, and I'm pretty happy about it, and everything goes according to plan. Or I don't have a match, and then I have a problem. And somebody needs to do something about it. So I have a second output. When you look at the query, I have a common table expression that will do that left join, and then one select into match where I don't have a problem. I'm finding that key is good. And the second one select into no match from that same CTE where I have a problem. And that's basically it. That's fairly simple SQL statements. And you know everything about semantics. So we are done. No, yeah, there's a couple of other things, but yeah, it's pretty simple. And let's see what you need to think about when you start writing that query. So the first really important point, and it's not specific to Stream Analytics here, but more about like stream processing, is when you're writing a stream processing query, you're writing a query that's going to be standing. What we mean by standing is continuous. It's going to be running continuously 24/7. Think about, if not exactly that, but think about an ETL job, a batch job running all the time, 24/7, never stopping. When you query a table in a database, so on the left is like, you're in Azure SQL, you're in SQL Server, you have a table. At some point, you can use a transaction isolation to say, take a snapshot, or here are the rules so that when my query starts, I can have a constant a set of data. I can apply my logic and then get the results and then be done. that's how it goes in a SQL database. That's not the case in stream processing. In stream processing, the data is coming all the time, and there is no expectation that it's going to stop anytime. We cannot use transaction isolation to say, okay, just taking a snapshot, looking at it now, and now no, that's not how it works. The query is running continuously all the time, 24/7. The data is coming continuously all the time, 24/7. So if I need, as long as I'm not doing any kind of blocking operation, so if just doing like projections, filters, those kind of things, the data can just flow through with like minimal latency implication, record showing up, simple projection, record showing out, and we're good. But as soon as I need to do any kind of blocking operation, so aggregations and mostly stream to stream joins, I will need some kind of time window. I will need to tell the engine that this is a sum over the last 10 minutes. That join between transactions and return, this is only over 2 days or 3 days. This is a key element that you need to keep in mind. I don't want to go into more details. I've put links that goes like deeper into that aspect because it's really interesting. But just need to keep in mind that aspect because we will have an impact on the language. Looking at the basic statement, it really we've put in a lot of effort to make it look as much as possible as T-SQL. So it's obvious, you have a select from, group by, we even have match recognized, which is awesome. And when you think about the typical query flow, the one we recommend, because you're writing, remember, you're doing an ETL job, writing with a single SQL statement, the query flow that we're expecting you to take, that's the one we recommend, is using common table expressions. So you do with, and then a couple of steps, 10 steps, 20 steps to do all the processing you need. And then a select into output, select into output if you need to reject or if you have alternative outputs. So series of steps and then a series of select into statements to output data to downstream. That's pretty much it. That's pretty much it. In terms of the functions we support, I'm not going to be reading all of those. Aggregates, require, group by, and of course a time window. That's as I just mentioned. The analytic function, average over, count over, max over, we have those plus specific ones. Conversion, we highly recommend try cast, which is basically cast, but instead of failing, because the query is running continuously, don't want cast to fail, because when you're writing a query in a database and cast fails, the query fails, and then you're like, okay, I'm going to write it another time, I'm going to fix it and do something else. The streaming job's running 24/7. If it fails, then you have an outage because your job's not running anymore. So we provide try cast, which instead of failing the job, will put in null. So if you see a null, and then you can make where try cast is null, that means that you have an error, and put that into a secondary output to do some post-processing. But yeah, try cast highly recommended. And I'll talk to it a little bit more after. And then we have a couple of specific functions that I want us to take a look at, starting with type management. So this is Stream Analytics has its own type system. So if you've been around a little bit, you know about integration services, you know about Data Factory or any kind of other ETL. Those ETLs, they are developed in a specific language environment framework, and they have their own type systems. So in terms of what is a bit, what are the numeric types that we support? Is it like small ints, tiny ints, big ints? How do we support floats? Do we support decimals, strings, etc., etc.? Stream Analytics, every other tool, has its own type system, and we've built it to be both minimalistic and to reduce friction, and to be as close as the SQL Server 1 as we could. So the types we support are bit, big int, and big int can be used for any kind of integers. Float, nvarchar max, no precision. Everything's an nvarchar max. There's no nvarchar 200. Everything's no problems of performance. Just go there. Date time, which is actually date time 2. And record an array. We will talk about record an arrays because they're specific ones. But that means when you think about from end to end your data processing pipeline, when using Stream Analytics, you need to think about everything that could impact your type management. The first one is I said, like when you're reading from an event hub, when you're reading from a stream, it's pretty much a table. Yes, it is a table, but contrary to tables, most of them don't have an enforced schema. So what you put into that stream, in that event hub, is like random JSON document. So it looks much more like a Cosmos DB collection than it looks like a SQL table. So it's a schema on read. It's not schema on write, which means that I can have types that vary over time. I can have even like schemas, like whole properties, fields that disappear and come back, or like even like multiple schemas cohabiting in a single event hub. And Stream Analytics needs to deal with that for you and solve that. But just need to be mindful of that. And so how you define that is what we call the serialization format. So an input event hub has a serialization format. You need to pick between JSON, Avro, CSV. CSV, everything's text, obviously, and it's flat. JSON, Avro, those are nested formats, and you have like different type systems. Well, you just need to know about those and what you want to do with them. Then, depending on those, they will map to a specific type in Stream Analytics. Inside of the query, we will do some implicit conversions for you. If you do a sum of a field without having explicitly casting it first to a numeric, we will assume that you knew what you were doing and implicitly cast it to float. Unless it's not, and then you will break the query and have an outage because we don't know how to deal with it. So highly recommend you use explicit conversions. We are back to try-cast. Use try-cast as much as you can. Then we do some output type mapping to the specific output that you're using. So how does our float goes to Cosmos DB, for example? Can you write one of our float to a decimal field into SQL? Yes, you can. There's another mapping table there that you need to take into consideration. And then, of course, depending on the service, what you can do and what types are supported, like records and arrays in SQL, not going to fly. So how do you want to process those? You need to think about. We offer capabilities, you need to implement them, you need to use them. And such functions to how to solve records and arrays, those are the ones that we're going to be talking for the next 3 slides. So records, what are records? Records are basically nested, an object that has properties. So here I have sensor readings that have 1, 2, 3, 4, 5 nested properties. Sensor readings is a record. So I need to deal with it. And an array, so sensor 03 is an array. It's an array of primitive types. Here it's an array of integer. But sensor metadata is also an array. Like it's between square brackets. It's a list of records. And here it's a list of records. Like it's not like simple integers. I actually have multiple records in there. That's most data that's coming from like a stream is under that format. And we are offering you SQL to deal with it. And I'm sure you know T-SQL up until recently was not really happy with that kind of like data format, processing JSON. So we have specific functions and capabilities. We've put them in the language that differ from T-SQL just because we needed them specifically for stream processing. The first one really is the dotted notation. If I want to get like sensor 03 from sensor readings, I can just do sensor readings.sensor 03. We offer the dotted notation so you can grab and extract that specific project, that specific property. But we have more than that. We have a list, and I just want to focus on 2 of them. The first one is, let's say I want to expand an array into rows. So here I have 12, -5, and 0 on sensor 3, and I need to unpack that. I need those to be one of each of those value need to be a single row. So how I do that in streaming SQL in Azure Stream Analytics is using cross-apply plus getter elements. So I'm reading from my input, cross-apply getter elements of sensor I, because I've prefixed input, dot sensor readings, dot sensor 03, and that's going to become SO3. And in SO3, I'm going to grab, like that's a keyword, the array value. And voila, it just gives me 1 row for each value of that table. It is a keyword array value because we also have array index, which can give you the position, if you need a position in there. The second one I wanted to mention is the same thing, but for records. Now I'm looking at sensor readings. I need to unpack those guys. I need 1 row for each of those properties. So here I'm going to be using cross-apply with getRecord properties, and I'm going to be unpacking i.sensor readings as SR. And here I need both, so same, keywords that we offer with scale record properties, the property name and the property value, because I just like having those values like rows without having the name of the property would be useless to me. So we also offer you the property name, so you can have that like neatly packed, and you can output that or like left join, group by, filter, do whatever in the following step, and just do what kind of processing you need to insert that into wherever it's going. Okay, so that was the first big chunk, type management. How you need to think about from end to end the different type systems you have and the conversion, implicit and explicit. So your pipeline is robust. We are dealing with ETL. We need to be like account to like the schema drifts and the anomaly that I can get into reading from a source that it's the schema on, right? Second aspect, where how I need to be able to process records and arrays, to unpack them, to be able to insert them and do whatever I need with them. Next aspect is temporality. So I mentioned that for stream processing, like there's always that notion of time. But actually we can define time. There's two ways to looking at streaming data in terms of time. One is the arrival time and the other one is the application time. So arrival time is when you look at data coming in your input event hub or like event broker stream, you can just look at the time, like the world clock time, and say, okay, this record shows up at 10:00. Well, that's going to be its timestamp. And any kind of time logic that I'm going to be applying from now, it's going to be about the time that that record shows up to my system. And we have a dedicated function that's called system.timestamp, which is really, really important and really awesome. That's going to give me that time if I need it. So if I just do select system.timestamp as T, I'm going to get that green clock. That's just the time at which the record shows up. And that's the default behavior. But when you think about it, if I'm looking at transactions coming in, I don't care about which time they showed up at. I care about when did my user actually, my customer actually purchase something and made that transaction. That's the time I'm interested about when I'm thinking about calculating any kind of like dashboard metrics about like the performance of my store. And that's going to be the application time. So now the time, that's the white clock, it's part of, it's a field in my incoming row, my incoming payload. How to recognize, promote that field as the timestamp is by using the keywords, the function timestamp by. So that's from input timestamp by and using that column name. And now what system.timestamp will return is the value of that field coming in. This is where we're expecting most processing to happen. And now that we have that, one thing that can happen is you may receive data that's either late, really late. Potentially one of those has a timestamp, a date that's from 3 years ago, or potentially one that's from the future. So how do you deal with those? Well, we have what we call time skew policies to add like some knobs so that you can say if it's too late in the past, then you drop it or you adjust it to now. And if it's out of order, if like events that are showing up like completely like the chronology is not respected, we offer you to like clean that up. The default options are good. Don't play with those if you don't know what you're doing. Our default settings are really good, so just leave them as is. And if you see some like wonky thing, then you can investigate and use them. But don't start there. Like default options are really good. The last thing I wanted to mention here is when you do that, the system.timestamp, this is a function and we are not using that because if following that time skew policy being applied, we change to timestamp. So let's say this one came in with a timestamp like 3 years ago and we updated it to now. It's the system.timestamp that we update. The my timestamp column, we don't touch because it's your data, it's your payload and you maybe want to do something with it. So my timestamp in that select star will still be 3 years ago. What will be moved to now is the system.timestamp. It's the property of that row. There is a system property. Just wanted to mention. Okay, so now that we have like rows are timed, they are timestamped, we can use the window functions. So window functions are used, and I know window functions are usually in SQL. They are like T-SQL used in relation to analytics function and how you can define like the sum over something. We are using the same words and we shouldn't, but that's just how they're called in stream processing right now, and maybe changing, but right now that's the name they're using for them. But here it's the temporal window functions, and they are used in the group by clause. So here is like, basically I want a group by, but I need to limit that group by in time because we cannot look at the, we need to know which depth of data we need to put in memory to look at, to calculate those average. So here I'm looking at like tumbling window. So that's 10 seconds intervals, one after the other. Then there's the hopping window, which is the same one, but recovering by here 5 seconds. Then there's the sliding window. Every time something happens, you have a new window. Then you have the session window, which is awesome when you need to look at user, like going through like some user experience and having or like shopping cart or whatever, like use group by session. And snapshot, which is just looking at a single point in time. So really useful, and you need to do a distinct at some point. We don't have select distinct, but you can do a select group by snapshot, and it will give you, of course, obviously the distinct values in a specific point in time. And just a little example here, like mixing things. Here we need to do a sum and average by key over a 1 minute tumbling window. So tumbling window, that's this one. So each one of those, every minute, I need to know how many records do I have. So I'm using the recommended approach of using a command table expression with multiple steps and then one single select into output. First step, select from my input timestamp by my timestamp. Here, I don't care about that after that. And I know I have system.timestamp, so I'm not even projecting my timestamp. Then step 2, I'm doing my actual aggregations. So let's ignore those first 2 rows first. So my key, group by my string, my sum, account from step, group by tumbling minute 1. Talked about that. So what are those 2? Those are giving me the window start and the window end. So when those value apply, because I need to know that it's between minute 0 and minute 1 that my count was this one for my key. So I'm going to use system.timestamp. That's going to give me the window end, because that's when that row is emitted. That row actually is a message that's timestamp at the window end, and it just have like a meaning, a semantic that says it's actually a window result. So it covers 1 minute before now to now, which is basically what the logic is being explained. So with that, and then I was putting it to output, I will get from start to end by key a sum and a count. It's fairly straightforward when you think about it. And the thing is, you could say, oh, we could have written that into a single statement. We could have like collapsed that into a single statement. So select all like those fields from into my output, from my input timestamp by, group by tumbling my string. Yeah, you could have put that into a single SQL statement without using the CTEs. Thing is, when you're in VS Code and or like the portal and writing that query, we will give you data and metrics at the step level, which means to debug and troubleshoot what's going on and get performance metrics, etc. It's much better to have steps, so then you can drill in and know what's going on. So like having like that much like multiple steps and taking the time to write that query like that, which will make the experience much better. Okay. Before we go to performance, I just wanted to take a short break and have a look at a job, because we talked about job and we haven't looked at one. So let's do that. So let me go back to the Azure portal. I have one of my jobs. That's the one I want to look at. So always look at that. So that's a job I already had created a couple of months ago. Apparently there's a warning. Oh, virtual network. Let's not focus about that. My job is running right now, so I'm paying for that job. Okay, that's good to know. And looking at the metrics I see, so resource utilization, we'll talk about those metrics, but what I can look at already is that, can we do the last 30 minutes? Yes. It's reading around 1,000 events per second and writing around 1,000 events per second. Okay, so all good. But what is it doing? So it's reading, remember, input, query, output. That's what we need to do. It's reading data from a thing that's called, so that's an event hub. And that's an event hub. Yeah, here we go. With like request, messages, throughput. Okay, so that's my table. That's my input table. Remember, nothing complicated. Then we have a query. So we create the query. So select system.timestamp. That's my window end. A player tag. Okay, it looks like player data. I'm putting that into a Cosmos DB. Apparently, if I'm having like good naming conventions, I'm doing a count, sum of score with a ratio. So that's the sum of the score divided by the count. Okay, sum of player tag, total score error. Okay, why not? Group by player tab with a hopping window. So that's a hourly window. So I'm looking at the 60 minutes of data back in time, and I refresh that every minute. Oh, cool. And I want those records that have at least one, which is good. I'm guessing I tested that to have like more than one because it's weird to have just doing count star over one. Whatever. And then in outputs, where is it writing? It's writing to a thing that's called Cosmos out, and it's good. It's a Cosmos DB database. And if I look at my data explorer, my hourly scores. Yeah, okay. So I have an ID, a player tag, game played, the total score, the ratio, total score error. Okay. Awesome. So it works. It's cool. And that's my job, and it's running, and it's happy, and it's running continuously. So as long as I have whatever applications generating those logs from my game, writing into Event Hub, my query is running continuously, and writing to Cosmos DB in that case. That's pretty neat. It's pretty fancy. Okay. Now let's think about performance, because that's the last point I wanted to talk to you about, and what you need to think of when writing that query and building that job to be in the best position and to reduce your costs and be able to scale up if needs be. So Stream Analytics is a distributed system. It means that it's basically when you provision a job, what you provision is a cluster behind the scenes. We provision it for you. And potentially you can put as many nodes as you want to run your query in parallel. Really, the point is for that query and that task to be parallelized and run in as many VMs, nodes, computer as possible in a distributed fashion. How we do it is by scaling horizontally. So we are scaling out. We add nodes. We add computer to the cluster so that it performs better. We don't scale up. We don't make those nodes better. We scale out. There's two ways to do that, and it's not specific to us. Like distributed systems scale by using two patterns. One is to do a parallel, to run in parallel, which means, and that's the one at the top, I have my job definition, and I will, so I look at the individual tasks, and I will run all of those tasks in each of the nodes, but each of those nodes will only have to process a subset of data. And how do we call that subset of data? We call it a partition. Then there's the other option to do serial. So now, instead, each node will receive a subset of work, so a task in the logical topology, and they will process all of the data that needs to be processed through that task. So that's kind of the two modes. This one is partitioned. This one, we distribute the tasks. For us, for Stream Analytics specifically, the optimal topology, so the best way to scale out, is to do it via partitioning. So the one at the top, the one where we distribute the whole query and split the data. And we do that by partitioning. If your input is partitioned on partition count, partition key, and it's aligned with the output, and the partition key, either there's no aggregations, no blocking processing, or the group by is on the same partition key, then we're able to dedicate a node for each partition, which is the best experience you can get in terms of scaling, performance, and all like sweet goodness coming from that specific setup. Really, that's the one you want to look at. And that goes to the point I wanted to mention about Event Hub. So you're not reading from tables, you're reading from Event Hub. But tables have partitioning when you think about it. Not exactly the same partitioning. And when we're talking about partitioning here, we are like, it's more akin to like the distribution factor of Synapse SQL. But let's not go there. Let's just think about like partitioning is about, I have a single table. As a user, when I query that table, I see a single thing, but I have a knob to tell the system that it can actually distribute data in a way that then when I will issue a query, it's going to be able to parallelize my work across each of those partitions. So typical use case, fact table in a dimension, in data warehouse, and I partition by time. So per year, for example. So when I do a group by year, that query can be split across multiple partitions, and I will get better performance because each CPU can access and address like the specific partition of that. Of course, it's a vulgarization, but like bear with me. Same concept here. I need to know that if I know that my Event Hub is partitioned, then I'm going to be able to leverage that to parallelize my processing. Okay. But the thing is, who needs to know about that? Of course, I need as a reader, as a consumer to know about that, but the producer, like the application that's writing to that partitioned Event Hub needs to know about that either, because it's the partition, like the producer that will respect the partitioning scheme when they send data to it. So it's kind of a contract between you as a consumer writing your Stream Analytics job on top of that Event Hub and the producer writing to that table. So contrary to partitioning in SQL, which is imposed by the system, and when you're writing to it, you don't need to care about it. Here, the situation is a little bit more complex. And if we go back to my input and we look at my Event Hub, that's this one I'm reading from. That's my table. I can see that I have 8 partitions. Okay, cool. That's already, I know that I have 8. That's important. So I know that I'm going to be able to scale up because there's multiple partitions. If that was 1, I cannot scale up because I have 1 single partition. So I cannot like put more nodes because 1 node can at minimum read from 1 partition. But now what's missing is the partition key. Here, I'm doing round robin. So I'm sending in data randomly to the partition. So it's not optimized, but it's good. It's good enough. But we will see that at some point, you need to know about that partition key, because if you do a group by on that partition key, you need to know about that. Else you may end up in a situation where you're shuffling data all over the place. And we'll talk about that. So anyhow, back to Stream Analytics, we support those 2 modes, both partitioning and per query step. So when you create a job, we ask you for a streaming unit value. So I think default is 3 now. 1, 3, 6, it actually the job will run on a single node or a fraction of a node. 1/6, 1/2, or 1 node, 1, 3, 6. But when you go to 12 streaming units, you're actually running on 2 nodes, 2 times 6. 18 streaming units, you're running on 3 nodes. Okay. When we distribute that node, if you go and start your job at 18, we will need to decide which modes to use. If we can do partitioning, we will always do partitioning first because partitioning is much, much, much better. But we will check those requirements for you. We'll check that the partition count's good, the partition key is aligned, query is good, output's good, everything's aligned, check, everything's green. We can go partitioning. It's going to be like that. How you can see that is you can actually enable auto scale and you can change live, you can change the scale. You can go from 18 to 12 to 6, back to 18 to 20, whatever. You can change that scale live without stopping the job. If you need to stop the job to change the streaming unit count, it means that you're on the second mode. You're running distributed along query steps, and we cannot do that live because it means redistributing the topology, and we don't have that yet. We don't support that yet. Highly recommend that you think about those aspects. How many partitions you have in input, line that up with how many partitions you have in output. Cosmos DB is magical because it can provide any kind of partition count you want. Event Hub needs to be aligned. SQL, you need to tell us like how like that the partitions are aligned. Like there's a setting when you set up the SQL, Azure SQL and Synapse SQL, like destination output, you need to let us know that you've done the work of partitioning the table and making that like it should. Yeah, and the query. It's important too. And I'll talk about that just in the next slide. To get there, I need to talk about one last concept, which is stateful versus stateless processing. So when we're doing stateless processing, we're looking at one event at a time. So if you just do a projection, a where, a left join on a reference table. So not a stream to stream join, but a stream to table join. Like for routing, any kind of those aspects, you are stateless. And what it means is you don't need to maintain anything in memory. When you have that event coming in, you have everything to make a decision, implement your business logic, and then generate an output. Contrary to stateful processing, where you actually, let's say you're doing a 10-minute average, tumbling window average, you need to keep in memory 10 minutes of data. So when you have that last event in the time window coming in, you have those last 10 minutes to output the result. So that's stateful, and it's needed for streams to stream joins, temporal windowing, aggregations, machine learning, like any kind of those aspects, they will need to be stateful. And it's important because stateful obviously requires a lot of memory. And since we don't scale up, we scale out. How to add memory to the system is by adding nodes and distributing your data across multiple nodes. So using partitioning, that's how you make a stateful computation as performant as possible. But sometimes you can't, because in my case, I have my, let's say I have random, like the producers, at least my event hub is partitioned, but it's random partitioning. It's just sending that in round robin, like randomly. I cannot do the group by product and do a stateful processing, because in input, the partitioning is not respected. So I will need a first layer that will repartition. So do some cleaning, potentially that left join I showed with the product ID, and do some repartitioning. And if we do some repartitioning, then I can have an intermediary new event hub that's actually partitioned by production ID, which can then be used as a source of a second Stream Analytics job, which has that big group by product ID that keep everything in memory. And this one's going to be partitioned. This one's going to be distributed. Well, it's stateless, and stateless can actually be partitioned also. So everything's going to be partitioned. This is actually a much better place to be than having one single job that does everything. And you're going to be able to have like lower your cost and have better performance by doing two jobs like that with an intermediary event hub, but one single job that's going to be struggling because the data is not partitioned properly. So just a thing to keep in mind. If you're saying like, oh, this is too expensive, the latency is not good, my metrics not good, it may, most often it is because of something like that. The fact that the partitioning is not aligned and things are not going. And how you detect that on point, that's via monitoring. So you can use logs and metrics, both in the Azure portal and VS Code. One really important thing is you need to enable them. Like pretty much every Azure service, you need to enable diagnostic logs to log analytics for a better logging experience. So every job you create, enable diagnostic logs. They are not enabled by default. Please do it. It's going to be much easier to troubleshoot and understand what's going on with your jobs. The metrics to follow, we have a long list of metrics, but the one that are important to me and I'm recommending you follow them proactively. Backlogged input events. So when your job is struggling, there's more data coming in that it can write out and process. It's going to start backlog events. Keep an eye on that because we have some memory and you can backlog some events, and we're working on additional features so that like you cannot run out of memory. But it may still happen, and at that point, the job will crash. So keep an eye on the backlog input events. CPU and memory utilization. We call it SU utilization, but it's actually memory utilization. So it's more to know about which one are more like CPU intensive, which means that potentially if you're doing a lot of stateful operation and you are CPU intensive, mainly that there's something more in the query, some optimization to be done in terms of processing, moving up a filter. Memory utilization should be high naturally for like stateful jobs. But yeah, keep an eye on that. And watermark delay, which is pretty much the latency, really important to follow also, obviously. If the watermark delay goes up to 1 hour, 2 hours, 3 hours, something really wrong is going in and you need to solve that. And there's a couple of links I put in there so you can check out. Okay, that's pretty much everything I had to tell you. Now you know about Stream Analytics. You have all the high-level concept that you need to know about. You're good. You're set up for success. We talked about near real-time analytics, the use cases in the applications. We talked about streaming SQL, the functions, like the specificities of it. We talked about jobs and clusters. We talked about the differences between streaming SQL and T-SQL. So that's type management mostly. And so thinking about this is an ETL, you need to explicitly manage your types and how to deal with records and arrays. We talked about temporality, how you can type standby, you can do windowed aggregations, and all of those good stuff. And we talked about performance and which are the metrics, what will impact performance and which are the metrics that you should follow. You good? You're set up. So what next? We have tutorials, both on the Azure portal for you to use the Azure portal and for you to use VS Code. If you're still a little bit unsure about Event Hub, I highly recommend that you use VS Code and you use the local files option. You can actually do completely offline stream processing using Stream Analytics. VS Code, Azure Stream Analytics extension. You use local files and you do local runs. So you will run on local files, completely unplugged, zero cost, and you're going to be able to get acquainted with Stream Analytics and play and have like a fun time without needing to think about an event generator, an event hub, anything. That's the next step. Okay, you can do that just doing VS Code right now. And of course, learn more, Microsoft Docs. This is not from Microsoft actually. This is the one that's hosted on O'Reilly. Streaming 101. This is the absolute must read if you get started on stream processing. It really explains the temporality aspects. So really highly recommended. And how does it translate in Stream Analytics? That's actually the one I like. Don't stay stuck. If you have any issue, just reach out. We have a public email address. We reply as fast as we can. There's a Twitter account. That's the Twitter account for the product. There's a Stack Overflow tag. We have a Q&A. We have an extensive doc and always working on it. And you can create issues also on our repos, our repos that are followed by the team. Don't get stuck. Just reach out. We're here to help. And there's a community. There's already a community. The Q&A is active and there's people answering there. Okay, special thanks to Microsoft for sponsoring that edition of the data platform Virtual Summit. We're always that conference, so I'm glad I was invited. I hope you had a good time. What else is there? Oh yeah, follow the Twitter handle of the different organizer and the data platform one. And apparently there's giveaways. I didn't know about it, but that's pretty cool. So let's do it. Thank you very much. And I think hopefully we have some time for Q&A and I should be around. So yeah, let's see. Thank you. Bye.